Like any PhD scholars or MTech students are here?
Yes, sir. I am a PhD scholar.
Okay. So, what is your area of research?
Biomedical signal processing with the application of artificial intelligence means machine learning and deep learning I am using, sir.
Okay. Okay. And your affiliation?
VIT Vellore, do you know, sir?
Okay. Great.
Okay.
Yeah, hello sir. I'm Aditi Bhushan. I'm doing my research area on deep learning, but it is in agriculture, where we
Okay.
are going to help in disease detection, and also we will be suggesting the major preventive measures.
Okay,
So
like
I'm from
leaf disease detection, right? Leaf disease detection,
exactly,
something like that.
exactly, and we are going to take all cash crops and seasonal crops. So based on our, we are performing for a particular set of area, and
Okay.
I'm from Bihar, Muzaffarpur.
Okay. And your affiliation?
I'm also a research scholar.
No, your
Computer.
affiliation, institute.
Okay, okay. I'm Bhim Rao Ambedkar Bihar University.
Okay. Right.
Thank you.
Okay, so I think now we can start. So let me share my screen and just check the couple of things. Video, let me start, right? So is the screen visible?
Yes, sir.
Okay. Actually, still people are joining. Fine. Okay, now it is in full screen. So I think you can see it in full screen, right? Is it fine now? You can see the screen, right?
Yes, yes.
Okay.
Yes, sir.
Okay. So good evening, everyone. I welcome you all to this week 1 live session of the NPTEL course titled as Machine Learning and Deep Learning Fundamentals and Applications. So this course is provided by Professor M.K. Bhuyan, who is a professor in the Department of Electronics and Electrical Engineering at IIT Guwahati. And myself, Arka Roy. I will be your NPTEL PMRF TA. So I am currently working as a Prime Minister Research Fellow at the Department of Electrical Engineering, IIT Patna. So in these live sessions in each of the weeks, so this is a 12-week course. So for these 12 weeks, what the main aim of these sort of live sessions are basically. So in the week contents, you'll see that in the website, in the NPTEL website, the lectures will be uploaded. So the lectures are basically recorded by Professor M.K. Bhuyan. So he will be explaining each and every topic in bit detail. And in these live sessions, I will be trying to solve some of the numerical questions related to those topics that is basically covered by Professor M.K. Bhuyan. And at the same time, this particular course specifically, this machine learning and deep learning, apart from theoretical concepts as well, because theoretical concept is very much required. Otherwise, you will not be able to understand the latest technologies that have been came in the field of deep learning and machine learning. So you need to understand the mathematics that will be basically covered in the NPTEL lecture that is provided by Professor Bhuyan. However, in these weekly live sessions, I will try to give you some real life examples or will solve the questions through some real life realizations. Because in my opinion, this particular subject is like you have to pierce it through like getting the real life examples. Otherwise, it will just be monotonous. You have to do so lot of mathematics and all, so you'll get frustrated. So the main point is that you have to have some sort of implementation background as well, because anyway, whatever you'll be learning. For example, in the upcoming lectures, you'll see that the very recent architectures like UNet for medical image segmentation, generative adversarial neural networks. So the core deep learning part, the understanding the theoretical concept is okay, but at the end, after reading all these things, like all the deep learning based things, you will try to, your main intention should be that you will be able to implement that thing. So one part is basically understanding the mathematical concepts. At the same time, you should be able to implement those things. So what I have planned is basically, apart from solving the questions, I will try to show some of the implementations as well in Python using TensorFlow or Keras or PyTorch. So if that is also like if I get time, because we have to cover the NPTEL norms as well, because as per NPTEL, the main task is basically to solve the weekly questions. And apart from that, if I get time, I will try to show you some of the implementations. So this is the second time I am taking the deep learning course. The previous deep learning course that I had taken is with Professor P.K. Biswas. So that was also under the banner of NPTEL Deep Learning. So there I showed some of the real life implementations as well, with some real data sets, some of the synthetic data sets. But over here also I will try to show, but the main constraint is time. If time permits, I will try to show as much as possible. Okay. So in this particular live session, we'll first go through some of the key concepts that is basically covered in week 1. So the point is that I will not be covering each and every concept, because that is out of my scope, because within 2 hours, it is not possible to cover the whole thing. But I will try to pick up some queries that is basically floated in the Q&A section. So in the NPTEL website, you will see there is a bar is there in the task bar. You will see there is a tab called Q&A. So you can go there. If you have any query, you can post it there. So if you post it there, I basically look at those questions and I will keep those questions in my slides. So if you have any query, you can post it there and I will keep it in my slide. Okay. So today also I have kept some of the things that is basically some of the queries that is basically raised by some of the participants of this particular course. So we'll see those things, and that will be a glimpse overview. And at the same time, we'll see some of the numerical problems related to week 0. So let me tell you, the week 0 quiz that is there, you will not get any marks for this. Like they will show you some marks, but this marks will not be calculated. That this marks will not be considered as the final marks calculation, like if you give the final written exam. So week 0 is basically a dry run for this particular course. Whatever prerequisite you just need, that is basically there. So like some of the questions related to linear algebra, some of the questions related to calculus, probability, etc. That is very much prerequisite that you need to have for this deep learning and machine learning course. And then we'll try to solve some practice questions for week 1. So you'll see that in week 1, currently you'll see that one assignment is live. You need to submit that assignment within the due date. Then only you will get the marks. Otherwise, you will not get any marks for week 1 quiz. So I will not solve the entire or like the live quiz. Rather, I will take some practice questions for week 1, and then I will proceed with this. And in the subsequent lecture series as well, so for the weekly lecture series, I will follow the same pattern. So we'll do some quick glimpse of the weekly content, and then I will try to solve some of the practice questions. And through those questions, I will try to develop some of the core ideas, because you'll see majority of the questions, even in week 0 as well, you'll see some of the questions like finding solution of the system of linear equations, but they do hold some really important properties that you have to understand and that you have to visualize or intuitively get some idea out of it to get to know more about the machine learning and deep learning concepts. Okay. Okay, so the first thing that comes into mind, so what is the difference between machine learning and deep learning, so to say? So there is another paradigm that is basically artificial intelligence. So artificial intelligence is basically the bigger set. This is the bigger set. So artificial intelligence basically came first in the literature. And why it was required, it is basically, for example, if you are doing a job, which is basically you have to scale it up, like scalable job that you have to do. For example, you are trying to find defect in between some of the products that is basically manufactured by a company. So over there in artificial intelligence, you have a human, who has the prior knowledge about that particular work, that particular product. Let's say some shaving foam. So he knows that what are the compounds that is basically used for that, for constructing that particular shaving foam. And then he or she will do some tests, and he will annotate that if, let's say, test number 1's result is such and such, and test number 2's result is such and such, then either you have to accept that particular product, otherwise you can reject that product. That means some dysfunctionality is there in that product. So that was there in case of artificial intelligence. So it is purely based on a human intervened hard coded program. Why I am referring to hard coded program? Because this particular person has some prior knowledge about this particular product. He has tested out some of batches, and then he had seen that if test number 1 has such and such report, and test number 2 also satisfies such and such report, then only you can accept that particular product that should be shipped to market. Otherwise, you can reject that particular product. So this is basically an if-else loop that you can think about. So this is a purely hard-coded intelligence. You are putting some sort of artificial nature there, but that intelligence is basically purely hard-coded intelligence. So to mitigate this hard-coded intelligence, the new paradigm came that is called machine learning. So over here, the main learning was done by this person, and that subject-specific learning is basically uh, that it was propagated to the machine through a hard coding technique. In case of machine learning, what we are expecting is basically we'll ask the machine to learn itself from the data, and then it will do certain predictions or certain decision making if it has to do. So that's why machine learning came. But over there also some really holistic drawbacks are there. So for example, one drawback could be in case of machine learning, you have to extract some features of from the data. If you see any sort of current deep machine learning applications, for example, a particular speaker recognition. So in CD or let's say in Alexa, so what they basically do, if you have to do some sort of a speaker recognition task using machine learning techniques, they acquire the signals through certain sensors. They have sensors, and then they collect the data, and then they extract some features out of it. Then they have certain classifiers or some machine learning model, so to say, and they train that particular model. Now the model basically tries to learn from the data such that it can do some prediction. Now the problem is, if your data that you are feeding or the features that you are feeding into the model, if that is not a good feature, and what do I mean by a good feature? That is, for example, you have two sort of features and they are distributed like this. Like this is X1 feature and this is X2 feature. And they are like distributed like this. So this is very difficult to draw up a boundary between these two classes. So this we can refer as a bad feature. Now, if you are feeding these sort of features into your machine learning model, so automatically, intuitively, you can understand that your machine learning model will fail to classify or predict the correct things. So the next paradigm came that is basically called deep learning. So in deep learning, we basically feed these data and we ask the model to learn something out of these bad data as well. So the deep learning models basically try to learn from the raw data, and from the raw data itself, it tries to extract good features by itself. So this is completely, there is no human intervention is required. You can give raw data, even you can feed the direct sensor data itself, and then from the sensor data, you can do the proper prediction, and deep learning can do it. Okay. So over here, for example, you can take for machine learning, let's say these sort of tasks you can do, very naive tasks these are, for example, cat and dog classification. So in cat and dog classification, let's say you are extracting two sort of features. Let's say this is X1 and this is X2. So for example, this is an image of a dog, this is an image of a cat. So from this particular image, you can extract texture-based feature, and at the same time, some color-based feature. So you can see that the color-based feature, if you take the color-based feature from this particular image and this particular image, these are quite discriminative, as well as the texture as well. So over here, you can see that in the cat, in the body of the cat, you can see there are several striations. So if I change the color of my pen, so you can see that there is a striation, there is another striation. Here also there is a striation. However, in the dog's image, you can see that few striations are there, and those striations are basically a block of color. For example, this round shape is there, there is another shape. But in case of cat image, you can see these striations more frequently. So if you extract these sort of image features, you will see majorly these images from this cat and the images from the dog, or sorry, the features from the dog, they are quite distant apart. Now, if your features are quite distant apart, it is very much easy to classify these sort of examples by you plotting a line in between them. And this is basically called the decision boundary. This is called decision boundary. And our main aim in deep learning based task, as far as the classic task is basically a classification task, is our main job is to do or the job is to plot the decision boundary among the different sort of classes. So in case of machine learning, you can see that if you are extracting these sort of good features, it is very easy to classify. So my research area is also biomedical signal processing and deep learning. So you'll see that majorly I will be most of the examples that I will be giving that would have a hint of biomedical signals as well. So over here, I have collected the images. These are not the images. These are the signals of heart. Due to the closure and opening of the valves in our heart, there are 4 valves in the heart, in our heart. So due to opening and closure of the heart, you'll hear some of these sounds. These are called the lub dub sounds. So this is the lub sound. This is dub sound. So they are annotated as S1 and S2. So you can hear the sound using stethoscope. So over here as well, you can see there is an S1, there is an S2. But let's say a person is having some sort of heart valve disorder. So for example, valves basically works in this particular fashion. When let's say blood is in this particular region, so blood is residing in this particular region. Now when valve opens, blood will go down. So valve's work is basically when the blood will go down, it will make sure that after the valve closes, there is no blood in the upper chamber. If there is blood in the upper chamber, so it will create some sort of dysfunctionality in the heart. So if the valve is basically prolapsed or there are some other medical conditions are there, if the valve is having those sort of conditions, these signals have been generated. These are called murmurs, or these are also called the whispering sound. So you can see the signal has clear-cut difference. So if you extract energy, energy could be a feature from the signal. So for example, you can extract energy from here. Similarly, you can extract energy from here as well. So if you extract energy E1 and E2, so you can see that energy over here is pretty low because there is no other component over here. However, due to this particular region, you can see there is additional amount of energy that you can encounter. So energy could be a good feature to classify these sort of signals. But the problem comes in machine learning when you give some really difficult tasks. For example, this is also object detection class, object detection problem. So let me just ask you, is there any difference in between these two images? Like in terms of object, I'm saying the object that is present in these two images, are they alike or different? Just by visualizing it through naked eye. Are they looking alike or different?
They are alike.
They are alike. So that is what I was expecting. But the problem is quite challenging over here because these two are different sort of deers. So for example, this is this is called Enold, and this is so over here. If you ask a machine learning model, so for example, from these particular images as well, you extract the similar feature like texture based feature. So texture based feature for this particular image and this particular image will be almost alike because they look kind of alike in naked eye. At the same time, if you feed the color based information as well, you can see that the color based information is also quite alike in these two images. Now, if you extract these sort of features, which are basically they are not good as far as this particular problem is concerned. You can see if you extract the features for this particular task, you'll see that I think someone's mic is on. Please turn it off. If you extract feature in these two images, like this texture based feature and color based feature, you'll not be able to see some discrimination over there. More alike is that you will see all these samples, they are basically overlapped with each other or randomly scattered in the feature dimension space. So these sort of features, if you feed it in a machine learning model, obviously your machine learning model will not be able to classify it well. So to tackle these sort of problems, the deep learning phenomena that have been came. So the deep learning model deals with this raw data and iteratively, it basically tries to learn to extract good amount of features such that the features in the high dimension, they would be quite discriminative from each other such that you can get a good classification accuracy. All these things you will be able to see in the upcoming lectures as well. So there are several techniques like loss backpropagation, gradient descent based method. So I'm not going in with detail currently. So this is just a glimpse. Similarly, another problem is this one. So these signals are basically respiratory sounds. So when you inhale and exhale, again, if you hear the sounds from stethoscope, you will able to see, you'll able to hear those sounds. These are called the respiratory sounds. These are produced due to inhalation and exhalation of air in the tracheal region, for example, in the tracheal region and in the chest region. So over here, this particular signal belongs to healthy class, and this particular image, this particular signal belongs to asthma class. So again, my question is that are they looking alike or like some visual similarity or dissimilarity is there in case of healthy signal or asthmatic signal? Or you can encounter any specific sort of feature that basically looks promising to get a good classification accuracy? Or they are looking alike?
Most of the signals are alike from
Yeah.
both the image.
Yes. So most of the signals, if you see through the database as well, you'll see that most of the data will look alike. It is just like a random noise around the zero line. So if you use machine learning methods over here, you will see that majority of your tasks, you will not be able to achieve good amount of accuracy or whatever sort of performance metric that you are using. So deep learning plays a crucial role to tackle these sort of problems. And currently the research direction is totally shifted to deep learning. So very rarely you'll see these machine learning problems. These machine learning techniques are basically used for advanced problems, not like these sort of problems. There are several research papers that are till date that is basically written on ML based techniques. But the main challenge is that you have to have these good sort of features. But guaranteeing that whatever you are extracting as feature, they are good for classification, it is very difficult. In case of deep learning, you don't have to think about extracting features. The model inherently tries to extract good features by itself. Okay. So the next major thing that you have seen in this week's lecture is basically the Bayes classifier. Anyway, in week 2, if you have seen today, the week 2 content has also been live. So in week 2, Professor Buyan has discussed about Bayesian classifiers in great detail. So this is just a glimpse of the Bayesian classifier. So there are several sort of classifiers like minimum risk classifier, then you'll see minimum error classifier. So in this particular session, I'll be restricting myself to discuss the minimum error classifier only. So in Bayesian classifier, you'll see that, let's say you have two classes, one is salmon and one is sea bass. So in case of salmon, you can extract several features out of these particular images. And those features are basically the class conditional features. And why I am saying a class conditional feature, it is because X is, let's say X is our feature, and omega is basically the class. So let's say class 1 is basically salmon. So you, in the training set, you have the labels of the images. And for each of the labels of images, you are extracting some sort of features. So that means you are extracting features given the label. So that is why this is a conditional probability, or specifically, this is called class conditional probability. So you extract the class conditional probability for all the training samples that is there in the whole data set. So you are getting P of X given omega 1, P of X given omega 2. At the same time, for using the Bayesian classifier, there is another term that is called the prior knowledge. That is called the prior knowledge. So over here, the prior knowledge is basically prior knowledge of classes, P of omega 1, P of omega 2. So what this P of omega 1 and P of omega 2 intuitively means, or what are the physical significance of omega, P of omega 1 and P of omega 2. Let's say you are collecting this data set from two different regions in the earth. So let's say you are, for the salmon, you are collecting the data from the ocean part where the water is quite salty, and sea bass for extracting, for collecting the sea bass based information. So you are collecting these fishes from the part of the earth where like lakes and something like that, or small ponds like that. So where the water is predominantly kind of a sweet water. So you can understand that there would be some bias in the data extraction process itself. So you can say that if you, most of the data for the salmon class is basically collected from the salty water, and most of the data for the this particular sea bass kind of fish is basically collected from the sweetened water. So there is an inherent bias. So if I just give you a random, if I just randomly ask you that I have collected a salmon information from I went to a place in the earth crust where most of the water that is present there is this salty in nature. So you can think that if the water is salty, predominantly what would happen is basically the fishes that would be there is high chances are there we will see salmon fishes over there. At the same time, if you go to a lake or pond, you might think that, okay, as the water is quite sweetened water, the chances of getting salmon is quite less. However, the chances of getting sea bass is quite more. So that means when you collect the data, it gives you some sort of prior knowledge about the class. So over here, the prior knowledge is basically from where you have collected the data. If the data is basically collected from the salty water, then predominantly P of omega 1 is high, because in salty water, most likely will get the salmon fishes. If you are collecting data from this particular sweetened water, then you can think that the chances of getting salmon is quite less. However, chances of getting this sea bass would be quite high. So that means these are called the class-based prior knowledge, or as we are writing in terms of probability, these are also called class prior probabilities. And lastly, out of these two, you basically try to extract at the testing set, you train your model using this particular P of X given omega 1 and this sort of prior knowledges of the classes. And in the test time, what you have been given is basically you've been given a fish, but you don't know what is the label or what is the class identity of that fish. You have trained a model. This is a machine learning model. So to say, this is a Bayesian classifier. So this Bayesian classifier is basically trained at the time of training. So if I just use this red marker for the training path, this is training path. And for the training, you have used P of omega and P of X given omega. Because at the time of training, you knew that I am collecting data from either salty water or from the, let's say, sweetened water. And I know that what is the label of that particular fish that I am collecting from these two places. Now at the testing time, let's say you are collecting some fish from a pond that is near your house, and you are extracting some features out of it. And then you are trying to predict through this trained model that whether the fish is sea bass or salmon. So that time, your main expectation is basically to get P of omega given X. Because now you have that particular fish. So this is the fish that you have collected. You can extract the feature. That means X you can extract, but you don't know that which class it belongs to. And that is basically your task is to that you given this sort of features and given the trained model, you want to predict that whether the fish belongs to a salmon class or a sea bass class. So that means you are more interested in getting these representations. So this is P of omega given X. That means you are willing to get the class given the features. So this is called the posterior probability. Okay, in literature, in several books, you'll find they call it a posteriori probability as well. So they put a and RIE. So this sort of nomenclature also you'll be able to see. And over here, this thing is only called sometimes prior probability. So the main thing is this is where you have to apply the Bayesian rule. So the Bayes rule states that P of omega given X is basically P of X given omega multiplied with P of omega divided by total probability. So that is basically P of omega, P of X given omega. And if I even write it in more precise manner, so it would be omega j, because you are really willing to know that which class it belongs to. So you can give a subscript of omega j. That means either it is omega 1 or it belongs to omega 2. So you see that this part for all the classes, it would be same. It is basically a scalar term, and it is basically adding the all proportionality of each of the classes. So this j basically varies from j equal to 1 to n. The n is basically the number of classes that you have in your problem. So this particular summation will be there, and this will create a equal create a equal effect in all the classes for all the classes. For example, if I am extracting P of omega 1 given X, it would be P of X given omega 1, P of omega 1 divided by P of omega 1, P of X given omega 1 plus P of omega 2, P of X given omega 2. Similarly, you can also calculate this P of omega 2 given X. So over there, the equation would be P of X given omega 2, P of omega 2. And the denominator part will be same as this one, because this is the equation basically tells us, the theory basically tells us. So our job as a machine learning engineer or deep learning engineer, your main job is basically to use the mathematics efficiently. If these two things basically gives you the same response, the denominator gives you the same response, then there is no need of calculating the whole lot of expression. Because anyway, whatever computer algorithm you'll be developing, that you will be using in sort of a hardware. So why you want to use more hardware, like you want to use more adders or multipliers in the hardware. So to reduce the computational complexity, as both the denominator part, this denominator part and this denominator part, they are giving you the same value. So you can discard this or you can neglect this. So your final equation that becomes P of omega 1 given x is basically P of x given omega 1 multiplied with P of omega 1, and P of omega 2 given x is equals to P of x given omega 2 and P of omega 2. And now if you have to, you calculate all these values, and then let's say this is giving you value lambda 1, this is giving you value lambda 2. If lambda 1 greater than lambda 2, then you can take the decision that your current data that you are feeding to the model, that basically belongs to omega 1. And if lambda 2 is greater than lambda 1, so that means you can say that x is belongs to omega 2. Okay. So there is another sort of representation that you can use to visualize this particular thing, that what we have written mathematically. So let's say you are extracting the a posteriori probability, and the a posteriori probability for both the classes looks like this. So in this particular axis, this is basically P of omega given x, and this is your input x. So with respect to input, you are plotting the a posteriori probability through this base rule. So let's say for omega 1, this is your probability density function. So this is for omega 1, and let's say for omega 2, this is the a posteriori probability density function. So can any one of you tell me that if my data, let's say whatever fish I have collected from the pond beside my home, if I have collected that particular fish and extracted some of the features, and this is where the feature is located in this feature axis. So what is the class identity? What is the probable class identity for this particular fish based on this particular curve? What class it belongs to?
Bus.
Sorry.
C bus.
The classes are omega 1 or omega 2?
Omega 2.
Omega 2. Yes, yes, that is correct. So what you have to do is basically you plot this particular feature over here in the one dimension, in the feature axis, and then you try to see the probability value. So this is basically the probability value for omega 2, and this is the probability value. Let's say this is the probability value for omega 1. So this basically P of omega 1 given x, and this is P of omega 2 given x. So now you can see that probability value of occurring in omega 2 class is higher than probability of the feature belonging to omega 1. So that is why you can say that your current feature that you have collected from the fish that you have collected from beside your house, so this belongs to omega 2. So this is how you can use the Bayesian classifier rule to classify the real life data. So there are several data sets available, like this salmon and sea bass data set. This is a very popular data set. So you can just use this particular formula to create these, to train a model, and then you can do the classification by your own as well. The next aspect is basically, let me just ask you that bias variance decomposition was there. If anybody has any issue with that, then I can explain. Otherwise, I will skip this particular. If you have any difficulty in understanding that particular concept, you can just tell me. So yes, the bias variance decomposition is that was there from the MSE expression. So if anyone has any issue with that, I can explain it again. Otherwise, I will proceed. Okay, it seems that there is no issue with this particular derivation. Okay. So the next important thing that is there is basically the Covert's theorem. So in machine learning problems, you'll see that in many cases, for example, over here also, you extract the features. You can extract features from these two sort of images. So they are dogs, but they have some class like intra-class variability. So this particular dog is basically a golden retriever class, and this is a dog of husky class. So now, if you try to classify, if you try to train a ML model, or let's say the simple Bayesian classifier that I have showed to you. So if you're trying to train a Bayesian classifier out of these two images, I mean, these sort of images. So the main thing is that whether your model will be able to give you correct classification or not. So for example, you can extract some features. Again, the P of X given omega 1 and P of X given omega 2. Let's say in this particular image, you'll see that if you extract color-based feature, then it is quite good because the golden retrievers have this golden furs. Whereas in the case of this husky, you will see that majority of the furs will be either grayish or whitish. However, at the same time, this particular dog in this particular image, it is also whitish in nature. So there is some sort of confusion that you can encounter. At the same time, the thing comes that is basically the prior knowledge, P of omega 1 and P of omega 2. Now, if you think that in the previous case, we are basically concerned about this omega 1 and omega 2, the prior probabilities specifically, like from where we are collecting the data, either from salty water or from the sweetened water. Now, in general, the husky images, the huskies basically live in the cold regions. However, let's say I have given you a synthetic data and I have manipulated the whole data. Like for all the husky images, I have put this same background as this particular golden retriever class. So even though as a from the human perspective, you know that even though husky belongs to the older region and the golden retriever can stay in the like normal planar region as well, so or tropical region as well. But the data set I have manipulated. Now, if you try to extract the prior probabilities from these background information, you will see that again there is a chance of confusion because P of omega 1 and P of omega 2, the prior probabilities, if it is based on the data from where you have acquired, they looks quite alike. They are looking kind of a tropical region, not like a discriminative, like this one could be a tropical, this one could be a colder region. However, over here, both the prior probabilities are looking same. So this is the point. Even if you encounter these sort of problems, if your feature that you are extracting, that is not good. Like if you are extracting features like this, where the features are quite overlapped with each other, there are some techniques by which you can solve this particular overlapped feature information and you can decouple the feature information such that your feature space basically looks like this. So from this particular data, you can do some sort of transformation and then you can get a feature space like this, which is quite distant apart, such that you can put a decision boundary over there. So the Covert's theorem basically states that in a classification problem, if the features, the low level features are not linearly separable, then you can do some sort of transformation and project the data into higher dimension. And most likely, when you project the data in the higher dimension or in the transformed feature domain, you will see that this non-linearly separable classification problem will become a linearly separable classification problem. So initially, your data, your features were not classifiable. Then using Covert's theorem, you have project the data in sort of another transform domain. Let's say this was X1 and X2 feature. Now you have transformed the feature into H2 and H1. And then you can see that these two distinct clusters such that the problem is now linearly separable. Okay. I think okay. So one real example would be, so let's say you have X1 and X2 and you have the outputs. So outputs are basically either class 0 or class 1. And if I plot these images, these features in the feature dimension, this is X1 and this is X2. So 0, 0 feature basically belongs to class 0. 0, 1 belongs to class 1. So this is 0, 1. Sorry, this is 1, 0 and this is 0, 1. And then the 1, 1 feature belongs to class 0 again. So is this problem linearly separable? With a single straight line, is it separable?
No.
Yes, anyone?
No.
No. So either you need to employ any nonlinear boundary like this sort of nonlinear boundary, otherwise you need two sort of straight lines. So this is where the problem has now become a nonlinear problem, a nonlinearly classification problem. And can any one of you just tell me that it is a basically truth table. This is a truth table of which logic gate?
XOR.
Yeah, this is from XOR gate. So now I can use Covert's theorem, and now we can really check that whether the Covert's theorem, what the statement is there, that is really applicable in the real life problem. So X1 XOR X2 is basically X1 X2 bar plus X2 X1 bar. So I can do some modifications like X1 bar and X2 bar. So this X1 bar multiplication will give you 0, and likewise over here also you will get 0. So adding this particular term basically gives no effect in the whole expression. So now what you can do is basically you can take the middle term factor and then you can do X1 plus X2 multiplied with X1 bar, sorry, plus X2 bar plus X2 bar. And this I am annotating as H1 and H2. Now, please tell me if I plot H1 and H2, how the feature space will look like. From these two X1, X2 input, now you can extract another two columns like H1 and H2. And please tell me that what would basically this feature space look like in the two-dimensional space.
H1 is 0.
Yeah, so
Or H1
over here it is 0, 1, 1, 1. And over here it would be
0.
0.
1, 1, 1. It is
Okay, I'm really relying on you. So
this one.
1, then
1,
yes.
1, 1, 1, 0.
Okay. So now if I just start plotting the features in the feature dimension. So over here now 0, 1 belongs to class 0, 1, 1 belongs to class 1, likewise. So this 0, 1. So this is where 0, 1 basically belongs to. This is 0, 1. Now 1, 1, the next two examples are basically the same. 1, 1 belongs to class 1, 1, 1 belongs to class 1. So over here, if I just plot the class 1, this is like 1, 1, 1, 1. And the last example that is basically there, it is 1, 0, which is also belonging to class 0. So this is 1, 0. So now tell me, is it now a linearly classifiable problem or not?
Yes.
Yes. So now we can draw a line, a separating line in between these two classes, and we can easily classify these two samples, the samples from these two classes. So this is the practical example of covert theorem. What basically the covert theorem statement basically means. You can project the existing data into some other higher dimensional data or some sort of feature transformation, and you'll be able to see that after applying these sort of feature transformation, you are able to get some sort of a representation which was not a linearly classifiable problem in the previous domain, but in the current domain, in the transform domain, the problem has become linearly classifiable. Okay. Is any confusion is there, or I can proceed? If you have any query, you can ask.
No, sir.
Okay, fine. So the next thing that people have asked in the query section or in the Q&A section of the website, that is basically ROC curve. So let me just give you a very short glimpse. Let's say you are classifying two classes. One is basically obese class, one is not obese class. And you are using some sort of a machine learning model. So you will be feeding the data. So this is your feature. So this feature is basically weight-based feature. So I'm annotating the feature as X. You have trained a model. So this model is trained. So I'm annotating as a MT. At the testing time, you are taking some data from, these are basically from rat classes. So whether the rat is obese or it is not obese. So you have taken the data from the test set, you have fed it into the trained model, and then you are doing the prediction, that is y hat. Your original label is y, and you are predicting it as y hat. If y and y hat are same, that means you have done correct classification. If y and y hat are different, that means you have done misclassification. And as because this is the, let's say there are two classes. So this classification is called binary classification problem. This binary classification problem. So what would be the size of the confusion matrix?
2 cross 2.
Yeah, so it would be 2 by 2.
2 plus.
So it would be like this. So this could be the predicted side, and this could be the actual side. So this is, let's say, obese, and this is not obese. And let's say we have developed the Y basically gives you some sort of a score, like it can give you a score like 32, any sort of a real value. Or I can write it like this: Y is following the real space. So if it belongs to a real space, it can adapt any sort of value, like it can adapt any value from minus infinite to plus infinite, and there is no limit in the value. But in many of the classification problem, you'll see in the later weeks as well, we try to use some sort of a probabilistic measure such that the probability value is has a finite range. It belongs from 0 to 1. It is not like something which has very abrupt value. So it is always uh, uh, prescribed that you use some sort of a metric which has a particular range, which has a particular range of the output value. So over here, let's say we are using a function which gives you some sort of a specified ranged data. So that is basically a sigmoid function. So how sigmoid function looks like? What is the shape of the sigmoid function?
Like an S only.
Like a S, yes. 1 second. Okay, so like a S only. So the expression is basically 1 plus e to the power minus x if your input is x. Okay, so it gives you the value in the range of 0 to 1. It gives you the value in the range of 0 to 1. And this is an asymptotic graph. So asymptotic means if you reach minus infinity, then you can get 0. If you reach plus infinity, then you can get 1. So asymptotically, it is reaching the uh, extrema value. So that is why I am not using the closed brackets. Rather, I am using the open parenthesis. Open brackets or parenthesis. Okay. So I can create a decision rule. So that decision rule could be like, if the probability, let's say you are plotting the functions, plotting the data points or the features in the feature space, and you are getting some sort of a probability value from this particular sigmoid function. Now from this sigmoid function, either you will get the value from 0 to 1. Now you can create a probabilistic measure and create a hard-coded function, like if the probability is greater than 0.5, then the class would be the obese class. And if the feature value is less than 0.5, then the class would be non-obese class. So over here, the main decision is basically based on the 0.5 probability value. If the probability value is greater than this, then the class is obese, otherwise it is non-obese. So based on this probability threshold, so this is called the thresholding technique. Thresholding technique. And why it is called thresholding? It is basically you are taking decision based on some sort of a value thresholding. If the value is greater than this, then you are taking the decision. Or if it is less than this, then you are also taking the decision. So using this, you can see that if the value is 0.5, so this red basically means the original classes of the samples. Red basically means the non-obese classes. So you can see that you are correctly classifying this particular sample. You are correctly classifying this particular sample. However, over here, what we are doing, whether it is a correct classification or misclassification for this particular sample.
Misclassification.
Yes. So that means this is a misclassification. this originally belongs to the non-obese, sorry, this blue one is the obese one. So this is originally belonging to the obese class, but as because you have set a threshold of 0.5, as the value is belonging, as the value is less than that one, so that is why you are predicting it as also the non-obese one. Here also, this is fine. You are doing the correct classification. For the last three cases, as you can see, the probability, it is basically giving you the probability value beyond the threshold point. So that means you are doing the correct classification for these three cases. However, over here also, originally it belongs to non-obese class. But as because it is giving you some sort of a probability value, or the sigmoid output is giving you very high value. So, and it basically satisfied the thresholding range. So it is misclassified as obese one, even though it belongs to the other class. So that means for each threshold, so I can vary the threshold. So for each threshold, I can get, so let us now first restrict ourselves for this 0.5 threshold only. So for 0.5 threshold, you have seen that you are doing correct classification, misclassification. So from this information, you can get a confusion matrix from this particular information. So this is a confusion matrix for threshold value is equals to 0.5. And from this particular thresholded confusion matrix, you can calculate the true positive rate and you can calculate the true negative rate or the false positive rate, FPR. So you can calculate these two values and then you can store these values. Similarly, you can change the threshold and then again you can see that what is the classification result. Again, you can get a confusion matrix. Again, you can calculate the value of TPR and FPR. This way, you have to start from this threshold equal to 0 to threshold equal to 1. And within this, you will get lot of confusion matrix. From all the confusion matrix, you will get these TPR values and FPR values. And then actually you basically plot the TPR versus FPR. So if you plot this for all thresholds, you get this different confusion matrix. For different confusion matrix, you get this different values, and then you plot this particular. You get this series of TPR values and FPR values, and if you plot this in this two-dimensional region, then you will get something like this. So this is basically called the ROC curve. So it is not like that you are getting the ROC curve from a single confusion matrix. You are using some sort of a thresholding technique. After using the thresholding technique, you are getting different confusion matrix. From different confusion matrix, you are extracting all these values, and then you are plotting all the values in the TPR FPR space, and then you are getting the ROC curve. So in majority of the cases, I have seen that student basically uses a notion, or this is basically a wrong notion, that they think that from a single confusion matrix, you can generate the ROC curve. It is not like that. You get the classification output as a probability distribution function or the probability value output. You use different sort of thresholds. For different threshold, you get different confusion matrix. And from all the confusion matrix, you try to create this particular ROC curve. And then you try to say that which of the threshold gives you the highest amount of classification measure or the classification accuracy. Like let's say this is threshold equal to 0, this is threshold equal to 1. But in between, you can see that this particular threshold you gives the best of both dimension. So now you can say that this could be the best sort of thresholded output, and I can use this particular threshold to classify whether the data belongs to obese class or non-obese class. And if you calculate the area under the curve, so this is ranging from 0 to 1, and over here also this is 0 to 1. So if you calculate the area under the curve in this particular region, so this is basically called the AUC value. So higher the AUC value gives you better confidence in classification. Lesser the AUC value, that means you're not able to classify it well. So if I just draw one example of low AUC, it would be like this. So over here, you can see that your AUC is quite reduced. And that is why you can say that this particular machine learning model cannot be adopted. For example, you can even use n number of machine learning classifier like support vector machine, random forest, KNN, etc. And you can plot these ROC curves. And from all these ROC curves, you can also say that which of the classifier is best suitable for your problem. You see the AUC values, and from the AUC values, you can say, let's say this particular graph is for SVM, and this particular graph is for random forest. So you'll see that AUC value for SVM is higher. So that means you can finalize your problem with SVM. You can reject random forest. Okay, fine. Any confusion here? Okay, so it seems that there is no confusion. So we can now directly move to the questions that is there. So I will solve the week 0 quiz. So in week 0 quiz, the first question is that they have given a matrix A, and you need to calculate the value of X for which the matrix is a singular matrix. So can you please define that? What is the what is basically singular matrix means?
Determinant is 0.
Sorry?
The determinant is 0, sir.
Yeah, determinant is 0. So the proper definition is basically the inverse of that matrix does not exist. And this is due to the determinant is 0 because A inverse is basically adjoint of A divided by determinant of A. So you can directly see the determinant value is equals to 0. So you can calculate X 0, 4, 0, 2, 12, 6, 0 is equals to 0. So over here, if I just solve it like this, so it would be 8, 0 minus 12 minus of X. So this is 0 minus 24. And then last one is 0. So this would be okay. So now you can solve this particular thing. So the second question basically states that you have a real square matrix AAT, and you have to comment about whether you have a real square matrix. A is a real square matrix, and you are calculating AAT. So whether it is symmetric, it is not skew symmetric, unsymmetric. So how would you approach this particular question? Is anyone? How do you approach this particular question? What is the answer of this particular question? I think you guys have submitted that particular quiz, right? Yes, anyone? You can just unmute yourself and then. Okay. So let's say the matrix is basically, this product is basically renamed as B is equals to A2. Now, if the problem is related to symmetricity, I can first see that whether BT is equals to B or not. If BT is equals to B, then I can say that the matrix is symmetric matrix. So let's do BT, B transpose. So A transpose of transpose. So what is the output of this particular operation? Can anyone tell me?
A transpose.
Like first answer this
It would
one.
be
Let's
A
say
transpose dot
A,
A transpose of A transpose.
let's say answer this one. AB transpose is given. So what would be the output of this one?
B
Transpose of
transpose into A transpose.
Yeah. So it is B transpose A transpose. So if you do B transpose A transpose, so you A transpose transpose and then A transpose. So it is basically A transpose. So which is basically B. So that means you have proved that BT is equals to B, and hence the matrix is symmetric matrix. Okay. Any confusion here? So this is the answer. Okay, I think there is no confusion. Okay, so the next question is A is a 3x3 matrix and rank is 2. So then AX is equals to 0 has what sort of solutions? Whether there is a trivial only one solution X equals to 0 or one independent solution, two independent solution. So what should be the approach for solving this particular question? Anyone? Yes, if you have solved this particular question, you can tell me that how you have solved.
There will be two independent solutions.
And what is the reason?
So since when we solve this, rank is 2 not of a third variable, it will be dependent upon the other two. So like I can solve it, but I don't know how to explain.
Okay. Any other mm, any other opinion to this particular answer? Anyone? Yeah, anyone else can comment about it. Whether you have any different opinion, you can just tell me. Whether you are sticking with the same solution or you have done something different.
I'm not able to explain the approach, but I got one independent solution.
Okay. So did you use any sort of analytical method or like any reasoning?
Yes, actually it was a sort of reasoning only that the rank was given 2 and it's
Okay.
already given A, X has to be 0. So I suppose that, and based on that, I analyzed that it should be like it should give me one independent solution. I'm not sounding logical right now, but that was just my
Okay.
analysis.
Okay. 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 So see, A has, because we are not given with the exact entries of A, so I am not able. So I am not defining generic representation of A. So I'm not putting any sort of values in the entries of 3x3 matrix. So what you can think of is basically rank 2 means there are 2 non-zero rows, right? So A, let's say this is the first row, this is the second row, and this is the third row. Out of these 3 rows, any of the 2 rows are non-zero rows. And 1 row is containing all zeros. So that is why rank is equals to 2. And you can see that nullity is basically dimension of matrix minus rank. So nullity basically means that how many of your rows in this particular rows or columns in this matrix is basically full zero matrix or null dimension. So over there, if I just do it analytically, so this would be 3 minus 2 is equals to 1. Otherwise, straightforward way, you can see that there is one row which is basically the zero row. Okay. Now, if I give you an example, concrete example. So let's say creating this particular example would be easy as well because they have given rank 2. So I have to design 2 rows like 1, 2, 1, and there could be another like 2, 4, 2, and another could be which has no relation with this particular thing. So it could be -1, -2, 0. So now to extract the value of rank, what we do is basically we try to reduce this particular matrix in a row echelon format or column echelon format. So to reduce this matrix in row echelon format, what we can do is basically R2 is equal to 2 into R1 minus 2 into R1. So you can see 1, 2, 1. And then if you uh, see that 2 minus 2 would be equal to 0. 4 minus 4 would be equal to 0. And this is also 0. So now we can see that one of the row has become vanished. It is containing only 0. That means this is the null space that we can get initially. Second one could be -1, -2, 0. I can again do a row echelon format. So this is basically, I can reduce it again. R3 plus R1 is equals to 1, 2, 1, 0, 0, 0. So this would be 0, 0, 1. So I would have stopped here as well, as because I have made this matrix in random. So I went this far. Otherwise, if you can see from this particular step itself, you got one non-zero row, you got another non-zero row. Over here as well, you got one non-zero row, you got another non-zero row. By the way, non-zero row means basically if any of the element in that particular row is non-zero, that is called non-zero. That is the notion of the non-zero row in case of row echelon or rank reduction matrices. So this, from this particular thing, you can see that rank is equals to 2, nullity is equals to 1. And as because you have 3 cross 3 matrix, you can understand there would be 3 variables. So if I just use this particular reduced matrix AG, so this AG multiplied with X would be equals to 0. So if I just write it like this, then it would be 1, 2, 1, 0, 0, 0, 0, 0, 1. And then you do x1, x2, x3 is equals to 0. So the first equation that we'll get is basically x1 plus 2x2 plus x3 is equals to 0. The second one is basically the full 0 thing. And the last one would be all 0, x3 is equals to 0. So now from these two, you got these two equations and 3 variables. Now the point is that can you extract sort of solution or dependent solution, independent solution, can you extract some of the solution out of this particular these two equations? So if I just solve these two equations, so you'll see that x3 is equals to 0 you have got already. So you can write x1 plus 2x2 is equals to 0. So x1 is equals to minus 2x2. So now you have got the solutions, that is.
Excuse me, sir.
Yes.
Yeah, sorry to disturb you. I just lost the connection. Can I know how would you derive that matrix A equal to 1, 2, 1, 2, 4, 2, and minus
It is
1, minus 1,
basically,
0?
the main thing is basically you have to create a rank 2 matrix, right? So rank 2 matrix, the notion is basically I started with this notion. So I started like you have to have 2 non-zero rows. One row should be 0, right? So my aim was while making this particular matrix is basically I will initially start with 3 rows, 3 non-zero rows with this one.
Hello.
Then somehow I have to create one single row which is completely 0. And this I can do by some sort of a linear dependency should be there in between these two rows. So you can see this row 2, this is row 1, this is row 2. Row 2 is basically 2 into R1. Otherwise, you can take any sort of linear combination of any of these rows, and then you can subtract it such that you can get all zeros. And the row third will be anything. Row third will be anything. It is just to ensure that there would be 2 rows which are non-zero, and the third row or any of these 3 rows should be 0. And how we can get a row equal to 0? So that is basically we have to have some sort of linear dependency over there. And this basically means that linear dependency. R2 is dependent on R1 with a linear dependency factor or scalar factor of 2. You can use any sort of factors. Generally, in the theory, it is basically written as like this: A into R1 plus A into R2 is equals to 0. So over here, this but A1 into R1, A2 into R2 equals to 0. So over here, A1 is basically 2 and A2 is equals to 1. So you can derive any sort of matrix. Okay.
Okay.
So if I now just do the solution, so I got this particular 2 equations. I solved this the first equation with the help of x3 is equals to 0 condition. So I got x1 is equals to minus 2x2. So I can write it like this now. X1, the solution space could be x1, x2, x3. I think I have to go to the next page. Yeah. So after solving the particular those 2 equations, now I can write x1, x2, x3. And I got the relations like x3 is equals to 0 and x1 is equals to minus 2x2. So I can even write it like this. X1 as minus 2x2, x2 and x3 is equals to 0. I can take x2 as common and minus 2, 1, 0. So now you can see that you can put this x2 with any sort of linear combination factor or any sort of scalar value. Let's say I am re-annotating as lambda minus 2, 1, 0. So now you can see that definitely you will get one independent solution. So your x1, x2, x3, it can be scaled, but definitely you are getting one independent solution, that is basically this values. X1 is equals to 2, x2 is equals to 1, and x3 is equals to 0. So this is why you get one independent solution. So any query?
Am I audible, sir?
Yes.
Yeah, sir, but this will be like infinity many solution, right? This one?
Yeah, so over here, if you solve this particular thing, if I give you this x1 plus 2x2 plus x3 equals to 0 and x3 equals to 0. So the thing is that
it's whether it will be one independent solution or infinitely many solution, or
it is basically, you can say that as because you are multiplying it with some sort of a scalar factor, you can get
okay.
representations like this. Like if I just write in a vector form, so this is 210, sorry, minus 210. You can scale it up with some other values. You can scale it down with some other values. So you have infinite solutions, but the dependency is this one. This is the main prime vector on top of which you are multiplying this lambda. So this is the dependent solution. This is the independent solution, sorry. This is the main, like the prime factor. On top of this prime factor, you are multiplying this lambda. So for example, you can multiply lambda 1 with this vector. Let's say this vector is v1, with this vector v1. And then you can also multiply lambda 2 with vector v1. And this 210 is vector v1. So you can see that the independent solution is v1 only. You can generate n number of copies out of this v1 by multiplying with some sort of scalar, but v1 is the independent set.
Okay, sir. So it will always if this 4 options are not there, then whether we have to.
Options are not. If it was written like that, you have infinite number of solutions. You could have ticked in the infinite number of solutions. But
Okay.
as because an infinite number of solution, as you can see over here, the infinite number of solution, they are dependent, right?
Right.
But they have written the term explicitly that whether you can get whether you can get some sort of an independent solution or not. So that independent solution is V1 only.
Okay, sir. And sorry, sir, like that time my mic was not working during that XOR problem, no, sir. So H1 you have made like x1 plus x2.
Yeah.
So like it is like just ORing, bitwise ORing, or
Yes. I'm not going deep into that because that problem you will see in the week 4 content that is related with basically you are doing some sort of OR representation and some sort of like NAND, like you can explore that thing, because in the when you will go to multi-layer perceptron lecture, you will see that there are certain gates, for example AND gate or gate. These gates can be you can classify these gates using linear solutions, like you will get something like this, you will get something like this. But in case of XOR, you cannot get a linearly separable. It is not a linearly separable problem. So the main point is that you can use some other features, and these other features are like you can use some other gates to create the OR gate. And when you use the other gates, then the problem becomes linearly separable problem.
Okay, so it will be always be like x1 plus x2, 1 plus 1 will be 1 only. It will not be 1 0. So it will be like bitwise ORing only.
Yeah. B2 is ORing only. Yes.
Okay, sir. Right.
Yes. So these problems when we'll be advancing the lecture in the subsequent cases, like when you will cross the initial phases of ML, like SVM and all, when the multi-layer perceptron, the basic artificial neural network, then you will see these sort of examples. So the next question is, you have this particular matrix and then you have to calculate the eigenvalue. So to calculate eigenvalue, you have to solve this particular formulation, that is a minus lambda I is equals to 0, where the lambda basically states the eigenspace, which basically comprises the eigenvalues. So if you start solving this particular thing, so this would be determinant. So this would be 1 minus lambda 1 1 Similarly, 1 minus lambda, 1 minus lambda. It is equals to 0. And then it is just you have to solve this particular thing. So 1 minus lambda whole square minus 1. Then it would be 1 minus lambda minus 1. And then the last one would be 1. So this is 1 minus lambda minus 1 equals to 0. Now, if you solve this particular thing, you will get 1 minus lambda, 1 plus lambda square minus 2 lambda minus 1. And then this 1 will be cancelling with each other. So this is plus lambda. Okay, so this was 1 into minus of, this is minus, this would be plus. So this is another lambda getting. So over here, if I just solve this particular thing, you will get 1 minus lambda. Over here, it would be lambda squared minus 2 lambda plus 2 lambda is equals to 0. If you solve this particular thing, you will get lambda squared minus 2 lambda minus lambda cube plus 2 lambda squared plus 2 lambda is equals to 0. So then you can see that some of the terms are basically cancelling with each other. And then you can do the following operations, like lambda squared is equals to lambda minus 3. So it is basically lambda equal to 0, 0, 3. So it is very simple. You have to do the analytical step. There is nothing difficulty here. So this is the final answer. Okay. So the next question is, you have 4 fair coins. So the fair coin basically means there is no bias in the coin itself. So it cannot generate like the probability of getting head and tail is 50% only. So this is called fair coin. So you are tossing 4 fair coins simultaneously. So what would be the sample space? Sample space. When you are tossing 4 coins simultaneously, what would be the sample space? Yes, anyone?
64.
Yeah, it is 64. So it is like, sorry, what? 64.
16 possibilities.
16.
Yeah.
So it is basically for one coin tossing, you are getting 2 spaces, that is head and tail. So for 4 such cases, you are getting 2 into 2 into 2 into 2. So that is 2 to the power 4, that is 16. Okay, and the sample space will basically look like head, tail, like head, tail. Up to it would be tail. So now the question states that the probability that at least one head and one tail turns up. So how many cases are there? We have total 16 cases. How many cases are there in which there is no, like, any of the head or tail is missing? So
14, sir. 14.
The 2 possibilities.
yeah, the probability, like at least one head and one tail turns up, there are these cases. Only these 2 cases are there. When you see all of them are giving you the same response. That means in this particular case, this particular thing is not following. At least one head or one tail. Here all are tail. Here all are head. So that means these 2 cases are the false cases for this particular event. So if this event is, let's say, annotated as A, so this A has sample space of 16 minus 2 is equals to 14. So therefore, you can calculate the probability of A is equals to 14 divided by 16. So this is 7 upon 8. Okay. Okay, so the next question is, you have a bag A, which basically contains 4 white balls and 6 black balls. You have bag 2, which contains 4 white balls and 3 black balls. So one ball is selected at random from one of the bags. So choosing one of the bags is basically a prior probability. So that means you have the data. It is the same thing like the Bayesian classification problem. You have pool of data and you are taking some of the data from, let's say, either salty water or sweetened water. So over here, the spaces from which you are taking the data is bag 1 or bag 2. So let's say probability of taking the ball from bag 1 is how much? Probability of bag 1 and bag 2, how much?
Probability of
Half.
Yeah, so this is half. So that means you are drawing ball from some of the bag. Okay. And now you are basically extracting a black ball out of each of the bags. So the thing is that you are extracting a black ball, let's say A given B1 and A given B2. So what would be the probabilities for this one? Sorry, you're extracting
6/10 into 1/2.
sorry for let's say black ball taken from bag 1, what would be the probability?
Six by 10.
And similarly for the second bag, what would be the probability value if you are taking black balls out of all the balls?
3/7.
3 upon
Yeah,
7.
so that would be 3/7. So now using the Bayes law, so the question is that find the probability that it is drawn from bag number 1. So now your probability is B1 given the ball collection. So A is basically the black ball. So the previously what you have is basically you are extracting, you given this bag 1, you are extracting bag black ball, and over here as well. So this was you are extracting black ball given bag number 2. So what you have to do is basically you have to use the Bayes theorem. So that is A given B1, P of B1, and then P of A given B1 and P of B1 plus P of A given B2, P of. So the answer is basically I'm writing the final answer. So if you solve this particular thing, you will get 7/12. So these are the values for the prior probabilities, and this is the value for the class conditional probabilities. And this is basically the a posteriori probability. Okay. So the next question is basically we have standard we have to extract the standard deviation of uniformly distributed random variable between 0 to 1. So what is the probability density function for a uniformly distributed random variable? What is the definition of the function?
1 by B minus A.
1 by B minus A. Yes. 1 by B minus A, and X range is basically from B to A. And elsewhere it is 0. So variance of X is equals to, can you give me the expression of variance? General, not I'm asking about the uniform distribution variance, the general expression of variance, how it basically can be calculated from expectation values.
E of x square minus E of x whole.
Yeah, so it is E of x square minus E of x ka whole square. So E of x is basically the mean of the system. So you can calculate it like this: x into fx dx within the specified range, that is b to a. So over here our b to a is equals to 0 to 1. So a to b is 0 to 1. So over here you can write x 0 to 1, and your f of x is basically b is equals to 1 and a is equals to 0. So this is 1 only. So x into dx. So x square by 2, 0 to 1, so half. And similarly, you can extract e of x square. So it is nothing but x square into f of x dx with the same limit 0 to 1. So over here it would be 0 to 1 x square dx. So x square dx is basically x cube by 3, 0 to 1. So it is basically 1 upon 3. So now I can write it like this. This is 1 upon 3 and this is 1 upon 4. So this is 12, 1. So this is variance of x. So you can get the standard deviation as 1 upon root over 12. This is the correct one. Okay. The next question is, if a random variable x satisfies the Poisson's distribution with mean equals to 2, what is the probability value of x equals to 2? X greater than 2, sorry. So what is the distribution function for Poisson's distribution? P of x equals to k. What is the formula for that? With mean is equals to lambda. What is the formula for Poisson's distribution? Yes, anyone?
E to the power minus lambda into lambda to the power k by k factorial.
Yes. So this is valid for x equals to q. Now what we have been asked is basically p of x greater than 2. We have to find the probability for p of x greater than 2. So what could be the alternative representation that we can opt for such that we can get p of x greater than 2? What we can write it in the other alternative format?
1 minus P of x is equals to 0 plus P of x
P of x
is equals to 0 minus
then
P of x is equals to 1.
then
That's it.
anything else?
Till x equals to 2, it will go.
P
Sir.
of
Yes.
x is equals to 2.
P of x equals to 2. So this is basically means that if you see the spectrum, let's say P of x greater than 2 means you are not touching x equals to 2. So this is also shown as like this. So if this is the real line, if this is x equals to 2 and you're writing x greater than 2, that means you are not touching x equals to 2, rather you are spreading from x greater than 2 means x belongs to 2 comma infinity. So that means you are not touching 2, rather you are from just after 2 you are stretching the range. So over here we have to calculate p of x greater than 2 means total probability is equals to 1 minus p of x less than equal to 2. So which basically covers these three spaces: x equals to 0, x equals to 1 and x equals to 2. And let me tell you one thing, this particular for this particular question, the answers that have been given, they are incorrect. So the correct answer is something else. So 1 minus, so this is e to the power lambda is equals to 2. So this is e to the power minus 2 and lambda equal to e to the power minus 0. So it would be 2 only. So then e to the power minus 2. Then you have 2 multiplied with 2 divided by 1. And then again, we'll have e to the power minus 2. And then it would be 2 square divided by 2. So it is 1 minus e power minus 2 minus 2 e power minus 2 minus 2 e power minus 2. So 1 minus 5 e power minus 2. So this is the correct answer. Even though in the website they have written 1 minus 3 to the power 2, had it been the question like you have to extract the value of p x greater than equal to 2, had it been the question like this, I think someone's mic is on. So had it been the question like this, px greater than equal to 2, if they had asked this one, so you have to restrict yourself till this point. And if you solved till this point, your answer would be 1 minus 3 to the power minus 2. So the question is incorrect, either in this particular region or they have given the wrong set of choices. So the correct answer is 1 minus 5 e to the power minus 2. Any query?
If 1 minus 3 power minus 2 will be the answer, means then what should be the conditions? X greater than 2.
I just explained. For example, if the correct answer should be 1 minus 3 to the power minus 2, they should ask this question. You have to evaluate the probability for x greater than equal to 2. If you are writing x greater than equal to 2, then you would have solved till this part.
Okay.
Is it okay?
Okay, so if the answer is 1 minus 3 e power minus 2 means the condition would be x greater than equal to 2.
Equal to 2, yes.
Okay, thank you.
Okay, so the next question also over here, they have again given the wrong set of choices, because sigmoid of x, sigma x, is basically written as 1 divided by 1 e to the power minus x. And they have asked to do the derivative of sigma of x. So I can write it as sigma dashed x is basically 1 plus e to the power minus x whole square. And then I can write 1 plus e to the power minus x multiplied with 0. And then minus 1, 0, minus e to the power minus x. So it would be e to the power minus x divided by 1 plus e to the power minus x whole square. So I can even decompose it. So it would be 1 minus e to the power minus x, and then e to the power minus x divided by 1 plus e to the power minus x. I can even write it like this. 1 divided by 1 plus e to the power minus x, 1 minus 1 divided by 1 plus e to the power minus x. So this is basically written as sigma of x 1 minus sigma of x. So this is the correct answer for this particular derivative. Otherwise, you can write it like f of x 1 minus f of x. The correct answer could be this one, or it could be this one. So this is just a numerical manipulation, but the correct answer is either this one or this one. But they have given something else. So this particular answer set is also incorrect. And this particular relationship is very popular. That is sigma dash x is basically sigma x and 1 minus sigma x. And the significance you will see in the deep learning section, because this particular term will come again in the deep learning part. We'll see this particular thing again. So any confusion in this particular question?
No, sir.
Okay. Okay, I have collected another set of some another set of questions as well. So this is your minus x plus 5y is equals to minus 1, x minus y equals to 2, x plus 3y equals to 3. So just by looking at this particular what you call linear system of equations, can you give me the answer directly, whether you have infinitely many or two distinct or unique solution? What could be the answer?
Unique solution.
And what is the reasoning?
Also, I have solved it with the help of metrics. I'm getting unique solution for.
Okay, so the first thing is this is a system. This is a system of linear equation with two variables. So the first point is you can solve the equation with two set of equations only. Second point is you can see if you write in terms of a matrix as well, if you take any sort of two equations and you try to write it in terms of matrix representation, it would be minus 1, 5, 1, 3. When I'm considering this equation and this equation, another matrix, let's say this was A1, this is A2. If let me construct another matrix with this equation and this equation, so it would be 1, minus 1, 1, 3, and the last case would be we have used these two, we have used these two. The last one is in between these two. So if I use these two matrices, so it would be 1, 5, 1, minus 1. So tell me that what are the ranks of this particular matrix? What could be the rank of this particular matrix?
Two.
2. So the matrix size is 2 cross 2 and the matrix rank is also 2. That means there is no nullity and a full rank matrix always has a unique solution. Otherwise, you can solve it through, like you can solve these two equations. Otherwise, the previous participant had said that she used system of linear equation and with matrix based solutions. So from there also you can get that particular condition. But the main thing is that if you construct any sort of matrix out of all these system of linear equations, you'll see that you will not be able to create any sort of non-full rank matrix. Each and every matrix will be a full rank matrix over there. Okay, there is another question. So this is another question. You have three equations, and this particular equation has given z equals to 2. And there are other two equations which basically comprises x, y, z, three variables. So again, my question is, can you just by looking at these sort of linear equations, can you give me the answer? What could be the possible answer for this particular question? Or you can just write a single one, like 1 or 2 lines and you can get the answer. But try to
B.
Yes,
It should be B.
Yeah, it should be B, because see, you are definitely you got a finite result for z equals to 2. This is a finite result. But for x and y, you have to use these two equations. Now you have the value of z, and over here in x and y domain, So again, if I just have to create a matrix of X and Y part only, it just create a matrix out of these elements. So this is 1, 2, and this is -2, -4. Can you now the question is, can you create what is the rank of this particular matrix first?
1.
1.
Yeah, so that this is rank 1. So nullity equals to 1. So that means there is linear dependency. So dependency is there. So whenever you have linear dependency, that means X and Y, they are related with each other. So it is like X is lambda into Y, or some sort of linear combination is there. So that means when you evaluate these two equations, you will get something like this. So it would be X, Y, Z, and it would be X lambda. So I can rewrite X as lambda into Y, then Y, and then Z is equals to 2. So now you can see that for X and Y, you can create infinite number of solutions. You can put any value of Y. You have n number of range for lambda. You can choose any sort of values for these two cases, and you can generate infinite number of possible solutions. So that is why Z has a possible finite solution, but X and Y has infinitely possible solutions. Now just recall the first slide where I had shown that if I just go to the first slide. So my main aim is basically with solving these sort of problems. The main aim is to create some sort of intuitive understanding of the machine learning based problems. So here, when I was discussing about the bad features and good features, when you see that features are overlapping with each other, so let's say this red features and blue features, they are overlapping with each other. So that means they have overlap, means they have some sort of dependency. If they were independent of each other, then they would have been differentiated. They would have separate clusters. They would be distant apart. But as because they are dependent, they have similar properties. That means they will be clumped together. In case of machine learning, and in the last problem, you saw that X is equals to lambda into Y. So that means if you are extracting a feature X and feature Y, and if they are related with each other, then these features are not good features. As because you can see there are some dependencies. So this equation gives you the notion of dependency. And from dependency, you can expect this sort of picture in your mind that this feature will be very clumsy. They will be randomly scattered with each other because they have some dependency. So that means we can refer these sort of equations or these sort of features as bad features, which has dependency with each other. So these things would be more clear when you see the examples in the later classes as well. But the main point is that you are classifying any sort of images or any sort of data using some sort of features. Now, if the features are not good, that means they are dependent on each other. They will be very clumsy, and it is not able to possible to create a decision boundary like this. So we are not interested with these sort of equations. Probably in week 4 or something, you will see that there is a technique that is called principal component analysis, that its main job is to remove these sort of dependencies, or these are called the redundancy, because there is no requirement of X and Y because they are related with each other. If I use these sort of features, the machine learning model will automatically get confused. Okay. So another question is, you have three linearly independent vectors, x1, x2, x3, three linearly independent vectors. If x1 is given, x2 is given, you have to evaluate what would be the value of x3 such that x1, x2, x3 are linearly independent. How you can do this? Yes. How you can derive the linear independency? You can give it a try. You can guess something.
Is there linear combination should be 0 if and only if the
Yes.
constant should be 0?
Yes, yes, yes. So theoretically, the linear independency means the linear combination. So first thing, linear independency, when independency thing will come, na? So you have to think that let us first write a linear combination of this, but these vectors. So the linear combination would be a1 x1 plus a2 x2 plus a3 x3. Now, if these vectors are having some sort of linear dependency, then this whole thing, this linear combination may go to 0. It would be linear independent only when a1, a2, a3, the coefficients are 0. That means they have no linear dependency. They have no linear dependency. Had it been like they have some sort of dependency, this linear combination would go to 0. If there is no linear dependency, only if these coefficients are equal to 0, then only you will get the linear independency case. So this is as far as the theory is basically concerned. So how you can actually relate with these options? So my first question is that whether A can be the correct answer or not. You have to check whether linear dependency is there or not. If there is any sort of dependency is there, then you can say that the option is incorrect. You have to search for these type of linear combination. If there exists any linear combination, that means they are dependent on each other. So if I just summarize it, any linear combination exists, then dependent set of vectors. Yeah, so whether A is the correct answer or not. Can you see any sort of linear combination?
No, sir.
X1 and X2.
C only, I think.
Yeah, so if you add x1 and x2, you will get x3. So that means x1 plus x2 minus x3 is equals to 0. So that means there is a linear combination. Likewise, what about option B? Can you see any sort of linear combination?
Yeah,
Yes, sir.
2x1 plus x2.
2x1 plus
Plus
x2 is equals to x3. Again, there is a linear combination. So what about option D?
X1 minus 2x2, sir.
X1 minus 2x2 is equals to x3. So now you can see there are three linear combinations are there, but if you try any sort of possible combinations, you can do n number of permutation combination, you will not find any existing linear combination in case of option C. So option C is the correct answer. So let me tell you, as far as the MCQ questions are being concerned, even if you know that theoretically a1 x1 plus a2 x2 a3 x3 should not be equal to 0 with non-zero A1, A2, A3, or vice versa, like only if A1, A2, A3 is equals to 0, then only you can get the linearly independent solution sets. You know all these things. But as far as examination point of view or MCQ problem solving point of view is concerned, you have to see the options, and from the options, you should try to get to the conclusions. Otherwise, it will take so much of time to derive these particular solutions. So you see the solutions, you see the options, and from there you try to reiterate or back engineer the problem. Okay. So the next question states that which of the following is strictly true for a two-class problem with Bayesian minimum error classifier with two different classes chosen as x1 and omega 1 and omega 2 with input vector x. So which of the, so I just have told you the Bayesian classifier. So that was the Bayesian minimum error classifier. So which is basically the correct answer from these four options?
D.
D. Okay, so yes, so we know that if x belongs to omega 1, so the probability, or specifically the posterior probability of omega 1 given x should be greater than the other posterior probability of the other class. Similarly, if x belongs to omega 2, it would be p of omega 2 given x greater than p of omega 1 given x. So over here, you can see that option D is the correct answer. Option C, you can see it belongs to omega 2, but it is writing the incorrect probability distribution function. Then they have written that based on the prior probability. Based on the prior probability, it is not possible. Because that is why I told you the example. Your training data is collected from the place on Earth where you get very salty waters like ocean, and the other set of data, which is basically for the sea bass, it is being collected from lakes and lagoons. And at the testing time, you are collecting a fish from a pond which is next to your house. So now you can see that there is a variation in the data. So if I just say that P of omega 1 and P of omega 2 from the training data set, one data set is collected from ocean, another data set is collected from lakes and lagoons. But at the time of testing, your data is collected from a pond residing near your house. So the prior probabilities are now changed at the testing time. So you will not be able to infer the class identity based on solely on the prior probabilities. You have to incorporate the class conditional probabilities as well. Similarly, if you choose to be x1 just based on class conditional probability, again you cannot decide that whether it belongs to class omega 1 or class omega 2. You basically require p of omega given x, which is basically p of x given omega multiplied with p of omega. Both these quantities should be needed to identify or to reiterate whether the sample belongs to omega 1 or omega 2. Okay, so this is the last question. You know that what is confusion matrix for binary classification problem? The confusion matrix is 2 by 2 confusion matrix. The shape is 2 by 2. So for 2 by 2, in many of the literature, in many of the books, if you see the performance metrics, so to say, they've been using the notion of 2 by 2 confusion matrix. They are not using like a multi-class confusion matrix where the class identity is greater than 2. That means it is not like the spam, non-spam. It is not like obese and not obese. There could be multiple classes. Now, problem arises in many of the situations I have seen that students just see the 2 by 2 confusion matrix and they basically get to know that how to evaluate TP, that is true positive, true negative, false positive, and the last one, false negative. So they know it very well how to evaluate these values for 2D case, or the 2x2 confusion matrix. Whenever they see this sort of n by n confusion matrix where n is greater than 2, then they basically stuck with this problem that how to extract the TP, TN, FP, FN values. And this particular confusion matrix, this particular problem I have taken to get into that particular scenario where you get the confusion matrix not as a binary confusion matrix, rather this is called multi-class classification confusion matrix, conf-mat. So in this particular case, the point is that how to extract the TP, TN, FP, FN values. And mind it, in case of multi-class confusion matrix, for each of the performance measures like accuracy, sensitivity, specificity, precision, recall, etc., all the things becomes class dependent measures. That means if you have to calculate precision, you can calculate for precision for class A, class B, class C, and then you can get an average precision. Similarly, for recall, if you have to calculate recall, you have to calculate independently, like for class A, class B, class C, and then you can get an average value. Average value of recall, average value of precision, like that. Okay. So here the question is, you have to calculate the precision of B, precision of class B, precision of class C, recall of class B, and recall of class C. Okay. So let me write this. This part is basically predicted one, and ground truth one is this one. So this is prediction side, and this is the actual side. Ground truth means the actual labels. So for class B, what is the value of TP? Yes.
Three.
Yeah, it would be 3. So this is that place. Your true class, when you have multi-class classification problem, here also you can segregate this problem into true class and like positive class and negative class. So your true class or positive class, true or let's say positive class, is equals to class B, and rest of the classes are your negative class or false classes. So the other classes are A, C. The other classes are A, C. Now,
Sir, one question, sir.
Yes.
Sir, here how to know like what is the expected value and what is the predicted value for each class? Like
what is the what is the predicted value? Okay.
because here class names are given like A, B, C, but for B
Yes.
class, what is the expected value and what is the predicted value, like class difference wise number?
So you can if I so there are two things that you can actually infer from this particular confusion matrix. So when you see the confusion matrix, just write these things. For the initial period, I would recommend you to go with the proper flow, that this is the prediction side, this is the actual side. So you'll be bothering about this fact that when you, let's say you are concentrated about class B. So you have to concentrate about total number of samples in class B. That how many samples are there in class B. Then total number of correctly classified or correctly predicted samples from class B. So how to get to know that how many number of samples are there, total number of samples are there in class B. So this particular site basically refers the actual class level. So if you go by this particular row, this basically tells you that how many number of samples are there in class B. So that means there are 1 plus 3 plus 1 number of total samples in class B. So that is 5. And how you can get the correct classification? So that is basically, you can see that your initial or your actual level is B, and over here you are predicting. So this is the these are the predicted one. So your actual level is B, you are correctly predicting it as B. So how many number of correct classification is there? That is 3. Then at the same time, your actual level is B, but you are predicting it as A. That means you are doing a misclassification. Similarly, your actual level is B, but you are predicting it as C. So therefore, here also you are getting another misclassification. So total correctly classification or correctly predicted sample is B equals to 3. And the original set of total number of classes that are there in the B class, or the expectation of total B class, is basically 9. Sorry, 9. This is 5. This is 3 plus 1 plus 1. So that
Sir,
value you
one
can
doubt
get.
is there, sir.
Yes, yes.
Sir, actually, how can we write that false positive and false negative?
Yeah.
in this
I will tell you that how to write that particular thing. But just tell me that this particular part is fine or not. That what I have just told.
Yeah, it's clear, sir.
It's clear, no? Okay.
It's clear, sir.
Okay. So the second part, when you see this particular, let's say I'm talking about single class only right now. So when you are concentrating on class B, so your class B is basically your true class. That means now I am referring it with the 2 by 2 confusion matrix. So let's say this is true class, this is false class, or this is negative class. So again, this is true class, this is negative class. And this side is basically the actual one, and this side is basically the predicted one. Now, in case of multi-class classification problem, when you are concentrating on a particular class, that particular class will be annotated as true class. All other classes would be negative class. Now let us try to find that what is the TP, TN, FP, FN, all those FP, FN, all those formulas. So if I just remove this particular thing, so TP is quite straightforward. So TP is basically if your actual level is B and you are predicting it as B. So that basically means it's true positive one. So over here, TP is this one. Now, in the 2 by 2 confusion matrix, TP is this one. Then this particular thing is basically false negative. Your actual class is true, but you are predicting it as negative. However, that is a false prediction. So that is why it is called a false negative. Now, similarly, for 3 by 3 case, we have to search for those false negatives. So how can I search for the false negative? So it is basically, if again I am referring to 2 by 2 confusion matrix, your original level is true. You are classifying it as negative class. So let us try to see your original label is B. So that is true class, but you are predicting it as A, which is a negative class. So that means this is a false negative. Similarly, your correct class is, your true class is B, but you are predicting it as C. C belongs to a negative class and you are doing a misclassification. So that means this is a false negative. Is it fine? Is this false negative part is fine?
Yes, sir. Yes, sir. It is fine.
Okay. So the false negative till this point, it is 1 plus 1 equals to 2. Now the second operation, the third operation is basically to find the false positive. So false positive basically means that your true class is negative, but you are predicting it as your actual class is negative, but your prediction is true. So that means you're predicting it as positive 1, but that is a false classification. So that is why it is called a false positive case. Now here we have to see that what are the false positive case. So over here you can give it a try that how to find the false positive case. From this sort of illustration, I think you can give it a try. You have to see that your correct class should be the negative classes, that means A and C, but you are predicting it as B. So that those would be your false positive. What are those cases?
One.
No. Again, if you see this particular part, now you are basically referring to the negative classes, but you are predicting it as true class. That means there is misclassification. That means you are doing a false positive encounter over here. Similarly, you try to see the negative classes A and C, which is basically predicted as B. What are those scenarios? When A and C are basically predicted as B. So those cases are the false positive case.
Zero, sir, then.
Zero. Yeah, it is 0. So if I just infer from this particular illustration, so our main target is basically to see the negative classes are basically predicted as the true class. And what are those cases? So our first negative class is basically class A. And we have to see, even if it is class A, I have predicted as class B. So this basically refers to this scenario. So this is the first, your FP. And this is my another, what you call the negative class. And this particular negative class is again predicted as the class B. So that means this is my another FP. So your FP is equals to 0. And what about the true negatives? True negative means your actual class is negative and you are predicting it as negative only. So that means there is no misclassification as far as negative class is being concerned. I'm not talking about the individual class. That is why initially itself I have clustered them into a single class that is called the negative class. Now you have to see what are those conditions where you have negative class and you are predicting it as negative class only. What are those cases?
It will be 3, sir, like.
So you are saying this one, right?
This one and the first cell and the last cell.
Okay, so 0 and 3. Okay,
Right.
this is partly the correct answer, but here is that you guys are basically looking at A comma A and C comma C as the correct classification, right?
C and C comma A also should be the answer.
Yeah, they should also be included because I am including them in the negative classes also. So I will be seeing A comma C, then C comma A comma A, and C comma C. Because even if A and C are distinct class, I have clubbed them in negative class. So all the predictions can be considered as true negative class. So your true negative will become 0 plus 2 plus 0 plus 3. So this is 5. So now you can calculate precision of B. Can you please calculate precision of B? Yes, anyone?
One, sir.
Yeah. So likewise, now this particular example was solely based on class B. Similarly, what you can do, you can calculate this for class C. And let me tell you, the TPFP, whatever these sort of quantities are there, TP, FN, FP, and TN. For 2 by 2 matrix, it remains the same. But whenever you encounter multi-class classification problem, this whole thing will change, as because when you'll be concentrating on, let's say, class A, so that time class A would be your true class and B comma C would be your negative class. So again, you have to do all these things. Again, you have to calculate what is TP, what is FP, FN, TN, etc. And then you can extract the values of precision, recall, accuracy, etc., etc. So this is a tedious job. But luckily, when you implement the codes, you will see that there is a library called scikit-learn. It is there to help you. You just write whether your problem is multi-class or binary class, it will give you all the values accordingly. But this is the analytical process that you have to follow. So likewise, you can calculate the other values. So I'm skipping for the other matrices. So I think we can, so this was the last one. So I think we can stop the session over here. If you have any query, you can ask.
Sir, whether those applications like you said, sir, like in programming, whether that also will be learning, sir, like?
See, in the course that is basically provided by Professor M.K. Bhuyan, so that is purely theoretical one. He will be showing some applications as well when you go to the deep learning part. So the lecture series have been assimilated in such a way that the initial couple of lectures will be purely mathematical. You'll be seeing very fundamental things about machine learning and deep learning, like this evaluation metrics and all. So one sort of example that you have seen, for example, if you are doing multi-class classification, in majority of the cases in books, you have seen 2-class classification. But when you do real-time implementation or real-life problem solution, then you'll encounter with multi-class problem. So there you can use these concepts. And at the same time, when from my side, I will try when like you'll be reaching the core machine learning part and deep learning part, I will try to show some of the implementations as well, if time permits. That is the main constraint. if time permits, I will show some of the implementations as well in deep learning, machine learning, both. Like how to write CNN, how to write RNN, how to create CNN plus RNN models, UNet architecture, all those things I will try to cover also here as well. But in the theory part, you will not get those things. You'll only get the theoretical aspect of each of these models, how to write the equation of these models, what basically they mean. So implementation I can show, but in the theory side, you will not see any implementation. Programming you will not see.
Sir, is tomorrow class there, sir?
So I will be taking these classes on every Friday with the same link. So probably by each Thursday, you will receive a mail from NPTEL that one class has been scheduled on Friday. So I'll be taking this class from 6 to 8 each Friday. And there is another TA, probably he will be taking on Saturday. So there are two TAs. One is me, another guy is from IIT Kharagpur, I think. So we both are taking the TA session. So the other person will be taking by Saturday. I think from 5 to 7. I cannot recall the timing exactly, but you must have received the mail as
Oh. Okay, sir.
well.
So these sessions, whether we can access afterwards also.
So the point is that NPTEL will actually give you a spreadsheet where you will find the video links of these particular sessions. So what I will do is basically I have recorded this particular session. I will be uploading this particular session in YouTube. You can check the channel name. It is by my name only, Arka Roy. So you can search my name and then you'll see several NPTEL playlists are there. So by tonight itself, I'll be uploading the video and NPTEL also will give you the link. At the same time, the slides that I have prepared and I have annotated, I will share them as well. So you'll be able to access the slides as well so that you can look through that what we have done.
Okay, sir.
Okay, so I think we can end the meeting here then. Let me stop share.